All right, hey everybody, Mr. Fortin here with your exit ticket. Now, hopefully you just watched that last lesson. It was a lot to take in 40 minutes, but you're gonna do this exit ticket, and guys, this is the same exact thing that's in your textbook for classroom exercises. So give this a shot on your own after watching the lesson. Please watch the lesson. If not, it's just sort of like you're just taking the answers from me. And that's not good because I want you to get these distance relationships. I want you to get the beauty of a power from a point to a circle and what exactly that means, right? Because there's a particular constant, a particular product that's associated with that point, regardless of how you draw your lines in. And that's pretty cool. Anyways, so we're going to do all 6 of these, 7 of these here, partially because I can just send my TAs out there, be checking your exit ticket, be like, why did they get so many of them wrong? No, you guys usually get it right. But it could be like, just watch this video, get it. Because you can make mistakes in these if you're doing them by yourself. So anyways, we'll do them together. All right, what I always say about all these here too, think about the point, okay? The point meaning the intersection that's forming the segments, right? The particular segments here. So I got this point right here. And this point, it goes 6 units to circle in that direction, and its opposite direction is 4 units. So its power is 24. That's not x, right? You're not asked to be solved for x here. But what would we know about x? Well, we go 3 in this direction. That point has the consistent power. A point has power over the circle, and it would be 3 times by x in this direction. Brings you to its same consistent power that's associated with that point here. Kind of the vertex of the angle that's here. We don't care the angle, we just care about these segment lengths here, okay? What's x have to be? X has to be 8, okay? So if you more literally use the theorem here, it would be r times by s, which is 24, has got to equal t times by u, 3 times x. Solve for x, you get 8. You're good to go, okay? Pat yourself back. If that's at all confusing to do, just watch the lesson video. Get background on why it is that way. All right, a little bit harder. We got some subtraction going on here. Well, that means this whole segment here is equal to 8. So if I know the whole segment here, yeah, you actually solve it. If you know the power of a point and you know what the whole segment length is here, you can find the individual segments. You can't, because you can make this whole thing is 8. I can make this x, and this would have to be 8 less that, which would be 8 less x, right? 8 minus x here. All right, power is 12. So I'm doing more traditionally, looking more like what the theorem looks like. So power of the point, 4 times by 3 would be its power, but that product would have to be equal to the other segments of the chord going to the circle. So 8 minus x times by x. Ooh, is this going to be quadratic? You guys might have to use the quadratic formula. You might have to factor. You might have to complete the square. All algebra 1 stuff. Come on, guys. Come on, guys. Got caught up on it somehow. I know I could spend a few weeks teaching it to you, but no, geometry is what I'm paid to do right now. Anyways, 8 times by x is 8x. Okay? X times by negative x is negative x squared. Okay? What am I going to do to both sides of my equation? So, hey, I'm going to go through this quickly, but when you're solving quadratics, you want to get x squared. The x squared with all the other terms, you want to set it equal to 0, because then you can use the quadratic formula. Why? Well, that's for algebra 1 time. That's our algebra 2. But anyways, what this is sort of reminding you of is, hey, that algebra 1 stuff you learned last year, should all learn. So it's pretty important. Add x to both sides. And hey, I had somebody last week who came in. One of my best students. Hey, you know who you are. One of my best students in all my classes came in being like, I forget how to quadratic formula, can you show me? And I did. I went through it, and I hope I did an okay job explaining it. But anyways, I'm moving my x squared to the left side. So I'm adding x squared to both sides of the equation. I'm going to move my 8x's over here, too. And you're going to see why in a second. I got minus 8x. Here I have plus 12, and that's equal to 0. Okay, that's equal to 0. So anyways, this is a quadratic equation, and I'm solving for the roots of it, right? The zeros of it. My polynomial's roots. So if I get it set equal to 0, I can do various things. I can use the quadratic formula, which states when ax squared plus bx plus c equals 0, then x equals negative b plus or minus the square root b squared minus 4ac all over 2a. Just kind of a mouthful. So anyways, you could do quadratic formula, but I see an easier way. I do. If you had me last year, you got it here too. I could factor this. Yeah, just factoring here too. Factoring you'll do in algebra 2 too. So anyways, I'll go over very quickly. This thing here, this polynomial here can be written in terms of multiplication. It can. X squared minus 8x plus 12 is simply equal to x minus 6 times by x minus 2. And if you've learned the FOIL method before, which a lot of people have, or generic rectangles and multiplying, you can double check to see that's right. X times x is x squared. Negative 6x times x is negative 6x, not negative 8x. Where did that come from? Well, negative 2 times x is negative 2x. Negative 6x minus 2x is negative 8x. Negative 6 times negative 2 is positive 12. How did I get that? How did I get my answers here? Well, my answers here is that I needed to get these two numbers to multiply to positive 12 and subtract or add together, right? Negative 6 plus negative 2 would be negative 8. So it adds there and it checks out. It works. Okay, so I actually have two solutions for x. Are we solving for x? Is that what it's asking for? It says solve for x. There'll be two solutions. Neat. That's one of the first times this year in geometry where I get two solutions, okay? So here I factored it. Zero product property. If this whole thing's equal to 0, what's my value of x here that would make the whole thing equal to 0? Well, it'd actually be 6. Right? If x were 6, 6 minus 6 is 0. In parentheses, right? Parentheses means multiplication. 0 times by, well, 6 minus 2 would be 4. But 0 times by 4, what's 0 times 4? 0 times 4 is 0. So anything times 0 equals 0. That's what's called the zero product property. So you just need to figure out what makes this equal to 0, x minus 6 equal to 0, and that's just 6. Okay, that's one of your solutions here. So let me put it up here. X equals 6, and here's your other solution, okay? Well, x minus 2. If I can get this factor, this thing in parentheses, if I knew that's equal to 0, that's going to be a solution because I have a 0 on that side. Anyway, zero product, the power of 0 that you learned in algebra 2, algebra 1. Very important here. X equals 2. Anyways, I just saved work here. And the x minus 2 equals 0 is what I meant to put here. Okay, anyways, so I get x equals 6 or 2. But the key thing is that the whole segment length is 8, so it kind of makes sense here. So 6 times by 2 is 12. There we go. We got it, right? So if x is 2, this is 6 over here. 2 times 6, yeah. So actually, x has got to be 2. This is drawn to scale. X is going to be 2. So I'm going to change this to 2. I'm just gonna put 2 there, right? Because I'm assuming it's like more or less to scale. So 2, right? See, this is much smaller than this. So I think this is where the 2 is. That's where the 6 is. But the key thing, what's the power of that point? It's 12. Okay, it's 12. And 6 times 2 adds to 8 and multiplies to 12. So you know it's right. All right, anyways, hopefully I was only quadratic because I wanted this video to be a lot shorter here. Because you already watched the lesson. You don't even watch 2 hours of geometry videos here, just an hour. All right, anyways, check it out here. Here we have, again, a secant. Here we have a secant here because this isn't a tangent because it's intercepting, it's intersecting 2 points here. So it's a little coordinate here. But anyways, so we're going to go power of the point. Power of the point. Point to circle times point to circle. Well, that's easy enough. This is simply going to be x times by 8. There's your power is 8x. But, hey, let's get a numerical power here. 4 times by 12, okay? Points to circle times point to circle equals point to circle times point to circle. Just an interesting thing, right? Interesting thing that relationship that these segments have. If I create 2 segments from that point, then they're both going to have that relationship where the external segment of the segment that I created times by the segment itself, the secant segment that is going to have the same product. So 8 times x has got to be the same as 4 times 12. And what do we do now? You guys all know how to solve that. This is what? Well, I divide both sides by 8. I guess it'd be 1.5 times 4. X equals 6. Right? Yeah, 6 times 8. That gets us to 48. 4 times 12 is 48, so x equals 6. Yeah, you're humming along. Well, I am. I feel pretty good about this. It's always nice when you get them right like that, like I just did. Hopefully you got them right here too. All right, check this one out, man. Oh, this is where they throw a little curveball at you. You got to remember, you got to look. Problems like this. Look at the point. Here's my point. What's the power of the point? It's not 6 times x. Wagging the finger. Why not? Because it's the exterior segment 6 times by from the point to the circle. Point to circle, point to circle. And x, that length here, isn't point to circle. It's just simply connecting 2 points of the circle, not the point that we're figuring out the power of here. So this is 6 times by 6 plus x would be one way we can express the power of this point We'll call it point P. And then 5, not 5 times 7, that's 35. 5 times by 12. Okay, times by 12. So this power is 60, right? Because that's 5 times 12. Okay, I can divide both sides by 6. That would make this 2, right? And then I'll get rid of the 6 here and make this 2. So now I got 6 plus x equals 5 times 2. That's 10. So that means x equals 4. And there we go. Is that right? Oh, yeah, it is right. Yeah, it is right. 6 times by 10 is 60. Yeah. So, yeah. Look, so it's longer. So this here, there'll be kind of this kind of opposite relationship here. If this is longer than this is, then this has to be shorter than that is. That's kind of interesting, isn't it? Because the product of this, if this is bigger, then this has to be shorter because it's going to equal the same product as this times by this. So this is shorter, this has to be longer. Anyways, that's one way I can tell that I probably did it right. X equals 4. Wait, I should put I'll fix that after. In post-production, I'll fix that so they say 4, not 1. All right, here we go, number 5. Here we got a secant. Look at that, we got a secant. So, no, sorry, we got a tangent. That's a tangent segment right there. So same deal, you can view this as, remember the original formula was r times by s, okay, x times by 9 equals t times by u, right? Those are those distances that you had in the theorems that were in the textbook. So what if t equals u? Well, that's just going to be t squared instead, okay? So we got 6 squared. The power of this point we can get from the squaring the tangent segment's length, that's going to be 36. And then that's going to be true for all secants too. External segment of the secant times by the whole secant segment. And it's going to be the same thing, so that means x is going to equal 4. Okay, you getting the idea of these problems? These are just some algebraic solving practice here after you've spent the time realizing and appreciating there is a geometric connection here. We got another 4. Hopefully I'm getting all these right. I would hate to edit this later. Oh, wait, no, there was one more. Guys, there's 6 problems here. You guys are going to miss it. You're going to miss some of these. You will. I'll have to edit this in post-production, I think. But, all right, check this one out. We got number 6. Okay, so we got this here. 2 times by 8. Okay, so same deal here, right? This is the same deal. This is easy enough. So this is 8. Point to circle times point to circle. Don't get screwed up by that. I mean, you're going to get screwed up. You're going to fall. You're going to make mistakes, but then you'll adjust from there here. Point to circle times by point to circle is the same thing as point to circle, and there's the only way to do it on that particular tangent line, so just point to circle squared, okay? So 8 times by 2 equals x squared, and this is why I say that this tangent segment's length is the geometric mean of what we got with this exterior segment and the whole segment of the secants here, because it would just be root 8 times 2 here, okay? 8 times 2. And that would simply simplify to what? Well, it's a 16 right here. So root of 16 is 4 again. We have 4 again? Is it 4 on all 3 of those problems here? Mr. Ford should check the textbook because these are just the classroom exercises that follow from the lesson that I just tried to lay out for you guys right before this here that you're watching here. Let's check it out here. Am I right? Is it 4 on like everything? What did I make a mistake on here? 4, 4, and 4. How about that? Right at the table. It's 4 on all those. That's easy enough here. Hopefully we see some work. So you're just not, give me the answers from your teammates here, or somebody else in the class. All right, you got to do it too. I know you're like, I've done enough, man. What is the deal with the subject? So, but just get it done. Here, look, enough. Proof. Draw. Like, don't even read the proof. Draw chords. Well, if I'm drawing chords in, they're introducing two line segments, 2 points. It's through 2 points. Exactly 1 line can be drawn. All right, a little posture from chapter 1. Using to justify the existence and uniqueness of particular segments we want to add to diagrams. Angle A is congruent to angle C. Well, that is in a circle. 2 inscribed angles. Angles are congruent. Are congruent if they intercept the same arc. That's it. They both intercept arc BD, so no A and C are congruent. Same deal with angle P. This is it. Yeah, so I didn't do this in the lesson video. Angle P is congruent to itself, so that's simply reflexive property of congruence. We're saying something's congruent to itself, not something's equal to itself. And then we have 4 is, well, I just said that 2 pairs of angles. One in this triangle, C and A, and another one in this triangle, P And this is all P is also in that one here too. So I'm saying these two triangles are congruent by a similarity postulate. Okay, right? Well, let's just see. What are we writing? We're trying to prove the power theorem here, that S times by R equals U times by T, right? So we got to do similarity to get there. That's what we're trying to do. So now we're working it back. What are we getting to? Oh, we got to set up that proportion. That's got to be definition of similarity, right? Definition of similarity. Okay, two triangles are similar if and only if the corresponding side lengths are in proportion. That's what we set up here. So R to T equals U to S. Okay, those are all corresponding sides. U is the smallest side on the larger triangle. S is the small side on the smaller triangle here. So that totally makes sense. Okay, last step to get to our power theorems, that along that secant segment, the whole secant segment times its exterior segments equals the same thing as the whole secant segment times by its exterior segment. So C is a little bit longer here, but shorter, the whole thing here. That would simply be cross multiplication or means extremes property, or I'll just write a property of proportions. Okay, and that's that. All right, exit ticket, get it out of the way. Guys, we're like almost there. Just do it. Let's do some math. That's what it's all about. Got to wrap up the year. We're going in. That's our last section, believe it or not, here of chapter of circles. Okay. Then I don't know exactly what we'll do for area and volume, but we got to do a few weeks of it at least here at the end of the year. Message me if you have any questions. Thank you. I think you're getting this on a Tuesday. I hope. Take care. Bye.